This is 3.6, zeros of polynomials. So in the previous video, we talked about long and synthetic division, and now we're going to do zeros of polynomials, and you'll see that the synthetic division and long division are going to be very useful here. So the first thing to kind of, before we start with the zeros of polynomials, I want to show you a really good theorem, which is called the Remainder Theorem. It's just a really cute trick that you can use instead of just plugging in a value into the function. So basically what the remainder theorem says is that if a polynomial f of x is divided by x minus k, then the remainder value is a value f of k. So basically what that means is, like, let's say you have this polynomial like 2x squared minus 3x plus 1, and I was dividing this by x minus 3. When I use long division, I'm going to get something, 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 plus the remainder over the divisor, right? Over x minus 3, right? So you're going to get something like that once I use long division or synthetic division, kind of like how we did last time. Well, basically what it says, what this theorem is saying, is that whatever this remainder is, it's basically just the function. And when I plug in, so if I plug in this number, this -3, well, in this case, it will be the opposite, which is going to be f of 3. That's going to give me the remainder. Okay, that's basically all it's saying. So, so instead of actually physically plugging in 3 in here, another way that you can find the value of the function is just by using long division, and then whatever the remainder is will be the function. So it's just another cute trick that kind of relates remainders with functions. So we'll just do one example of this. So let's say you want to use the remainder theorem to evaluate the following function. So let's say you want to evaluate f of x is equal to 2x to the 5th minus 3x to the 4th minus 9x to the cubed plus 8x squared plus 2, and I want to evaluate this at x equals -3. Okay, so we want to use the remainder theorem. So typically in the function world, before we even knew about the remainder theorem, one way that we can do is just literally plug it into the x. That's basically what it would be. But in this case, we want to use a different method. We want to use the remainder theorem to be able to evaluate this. So basically, if we go back to the remainder theorem, it just says that if you have this function divided by this linear factor, then all we got to do is just use long division, okay, to find the remainder. So the first thing is that this is not in the linear factor form. So what I'm going to do is I'm going to add 3 to the other side. So we got x plus 3. Okay, so I'm just basically adding the 3 over to the other side. So now what you want to be able to do is you want to be able to use either long or synthetic division. Okay, so I'm going to use synthetic division since it's probably the most fresh in our mind. So remember, in order to do synthetic division, we're going to look at all the coefficients. See here that the degrees are all there. So you have x to the 5th, x to the 4th, x cubed, x squared. We're missing the x, so missing x. And then we have this 2 there. Okay, so let's go ahead and write down all of our coefficients. So it's going to be 2, -3, -9, 8. We're missing the x, so we're going to write 0 as a placeholder, and then the 2. Now, what's going to go on the outside? Well, here's our linear factor. So this guy is +3. So this is going to change the sign to -3. And now we're just going to use long division, synthetic division. So we're going to bring down the 2. We're going to multiply this. We're going to get -6. And this is going to give me a -9. Multiply it again, you get +27. And then you add it, so you're going to get +18. Then we're going to multiply this 18 and this 3. That's going to give me -54. And then we're going to take the -54, add it to 8. That gives me -46. I'm going to multiply this out, 46 times 3. That's going to give me a +138. I'm going to bring this down. nothing happens here. And then 138 multiplied by -3, you're going to get -412. Added to 2, you're going to get -414, then -412. Okay, so this is my remainder term. Okay, so basically, if you go back to the remainder theorem, it basically says that whatever the remainder is, that's going to be me plugging in the -3 in there. So basically what this says is that f of -3 is equal to -412. And what you can do is you can go ahead and check it by plugging it in there. Now, why would we want to do synthetic division and not just plug in the value? Well, sometimes it's easier to just use the basic operations, which is addition and multiplication, as opposed to doing to the 5th power, to the 4th power, and all that stuff. So we're just using the basic operations that we've used before, that we've learned from grade school, to be able to find something that might be a little bit more complicated. But you're absolutely right. You can easily just plug that number in there and you get the right answer. But just a little quick trick to kind of be able to connect long division with functions. So one of the things that we have found so we're going to try to connect everything. So we found that we have some sort of polynomial. So polynomial p of x or f of x, whatever you want to do. One of the things that we found the end behavior. Okay, we're able to contact the end behavior or find the end behavior. We can find the number of terms, the total number of terms that this particular polynomial does. We can find the zeros and the multiplicity. And combining all of this, and we can even do y-intercepts as well. Combining all of this guy, we are able to graph. Okay, or a brief sketch of what exactly this polynomial kind of looks like. But we know that not all polynomials can be factored. So when we're trying to figure out the zeros of the polynomials, not all polynomials can be factored. Okay, so it's very, very difficult for us to figure out if a polynomial can be factored or not. Okay, so what can we do? Okay, so there's many different things that we can do. So here is another theorem that kind of relates back to the remainder theorem. And this is basically the factor theorem. And basically what this says is that if you can write a function the following way: x minus k q of x plus r. Okay, so basically the way that you're basically doing this, so you can write a function with this guy being basically the linear factor that you're dividing it by, which is what we call the divisor. This q of x is what we call the quotient. And this r is what we call the remainder. So you can always write a function like this. So basically imagine that when you have a function divided by this x minus k, what you're going to end up getting is the quotient. Okay, so whatever this divides by, plus the remainder over the x minus k. This is basically what we have. Okay, so the way that we get from the black part to the blue part is that we basically multiply every single term by x minus k. And you can see that these guys cancel each other out, and I'm left with this f of x is equal to x minus k, the quotient, plus r. So you kind of see this part. So one of the cool things that the factor theorem says, so we know that we can rewrite any function like this. Okay, so what the factor theorem says is that k is a zero of f of x if and only if oops, x minus k is a factor of f of x. Okay? And what this further implies is that the remainder is equal to 0. Okay? So basically, if I wanted to write this in different words, if x minus k is a factor of f of x, then when you use or when you divide, the remainder will be 0. Okay, so that's basically what it is. Okay, very, very important. So let me give you an example because I know this was a little theoretical. So here's going to be my example. So we want to show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30. Okay, so we want to show that this is a factor of this guy. So basically, if I wanted to factor this polynomial, x plus 2 will be one of the things that I multiply. So notice that this guy is going to be really hard to factor. We can try factoring by grouping, but there's not going to be any like terms that we can pull out. So we have to use something else. So we already know that x plus 2 it might be a factor. So what we want to use this factor theorem to try to show that it really is a factor. And the way that we're going to do it is to show that the remainder is 0. Okay, so let's start off by using synthetic division. So let's first write down the coefficients. So you're going to have 1, a negative 6, a negative 1, and a 30. On the outside, it's going to be the opposite sign of this guy, which is negative 2. Okay, and now let's use synthetic division. So you're going to bring down the 1. We're going to multiply this out, so you're going to get negative 2. This is going to give me negative 8. And this gives me a positive 16. And this is going to give me a 15. This is going to give me negative 30. And we get a 0. Okay? So, because we got a remainder of 0, what we say is that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30 because r is equal to 0. Okay? Now, furthermore, what we can do, now we're basically done with the problem. Now, why was this really useful? How does that help us factor this guy? Well, it does, because now what we can do is we can write this a little bit easier. So remember, we can write any function in this particular form. Okay, so basically this is what it is. So we can write the function that we have here, this x cubed minus 6x squared minus x plus 30. We can write it as x plus 2 multiplied by the quotient, and our quotient was this guy. So remember, this was an x cubed, so now this should be a squared term. It's going to be x squared minus 8x plus 15. And then obviously the remainder in this case is going to be 0, so this guy is gone. So basically what I did is that I can rewrite this entire polynomial that was really difficult to factor into something that looks like that. And now we can further factor the other part. So x plus 2, this guy can be factored as well. So this would be what, a 3 and a 5, and both negative. And now what we have is the full factored form of this guy. We can find the zeros now. We can find the multiplicities if they exist. So we can have all of this stuff. This is what we call is the full factorization or complete factorization. Okay, so we have the complete factorization of this problem. Okay, so let's do this other problem. So find the complete factorization for the function f of x equals x cubed plus 4x squared minus 4x minus 16 if x minus 2 is a factor. Okay, so if you want to try it out first. I'm going to go ahead and just do it. So even if you can try to factor this guy, which actually you can factor by grouping, let's just try to use the complete factorization of what we just learned. So we're going to start off by synthetic division. So this first part, so getting the coefficients will be 1, 4, -4, -16. And on the outside, we're going to change this -2 into a 2. So now we're going to bring this guy down. We're going to get a 1. That's going to give me a 2. This gives me 6, so this is going to give me a 12. This is going to give me an 8. It's going to give me positive 16, and you get a 0. So this gives you confirmation that this guy indeed is a factor. Okay? So now let's go ahead and just write it out. So we can write the function x cubed plus 4x squared minus 4x minus 16 as the factor x minus 2 multiplied by this quotient, which is going to be x squared plus 6x plus 8. Okay, then you can try to factor this guy out. X minus 2 is going to be an x and an x and a 4 and a 2. It's going to be a plus and a plus. So these guys is my full factorization. Okay, these are all my factors. If I were to ask for the zeros or the roots, it'll be x equals 2, x equals -4, and x equals -2. So you can do that as well. Okay, and based on this, you can find the end behavior. You can try to figure out what exactly this graph, how this graph looks like, and all that other stuff.